All right, everyone. Welcome to another episode of the TWiML AI podcast. I am, of course, your host, Sam Charrington. And today I'm joined by Adrien Gaidon, Head of Machine Learning Research at TRI, the Toyota Research Institute. Before we get going, be sure to take a moment to hit that subscribe button wherever you're listening to today's show. Adrien, welcome back to the podcast. We last spoke in May of 2019, believe it or not. And we had a great conversation. I encourage everyone listening now to check back to episode 269, where we discussed advancing autonomous vehicle development using distributed deep learning. A lot of what you were doing around ML ops and kind of productionalizing these large scale models. It was a great conversation, and I'm super excited to have you back on the show.
Sam, it's really my pleasure, and it's been too long, so I'm really glad we get to chat.
We're going to spend some time talking about, among other things, Datacentric AI and some of the things you're doing from a synthetic data perspective. But to get us started, why don't you reintroduce yourself to our audience, and we can spend a bit of time talking about what's new since May 2019 for you.
Yeah, okay, sounds good. Thanks, Sam. Hey everyone. My name is Adrien Gaidon, but you can say it in the American way, Adrien Gaidon. So I'm French, obviously, but I've been living in the Bay Area for 5 years now. I've been working in computer vision and machine learning for almost 14 years. 10 years in industry and 5 years at TRI as leading the machine learning research team there. One of the things that characterized my research is a lot about going beyond supervised learning. I have labeled data myself. Back in the day, people that know the Pascal VOC challenge, which kind of predated ImageNet, we're going to Oxford, famous visual geometry group, and clicking on pixels, and then my hate for labeling started around that time, and so that guided a lot of my research to because I think clicking on pixels is not the way to AGI. And so treating machine learning as a problem of really finding ways that machines can learn in a more efficient way without supervision. And so I did a lot of research on using synthetic data that I'm sure we're going to get to talk about today, but also self-supervised learning. Probably one of the things that we've been most well-known for, especially in the autonomous driving space, is we've been doing a lot of self-supervised learning and monocular depth estimation, which has been actually deployed in production and is used in various applications, not just autonomy, but something that is near and dear to my heart, which is saving lives. As you know, there's 1.3 million fatalities on the road every year. And so that's something that, keeps me up and motivated to work on this very important problem, in addition to, deep learning and everything being super, super cool. So basically that's who I am as a scientist and as a person. I love climbing, my family and stuff like that. And, with COVID, got to spend a lot of time with my daughter and actually learn some things about how humans learn, which I'm sure we could get to talk about that too. So yeah, happy to be here.
Awesome. Let's maybe talk a little bit about your focus as a researcher at TRI and some of the main things that you think about.
Yeah, for sure. So as I mentioned, going beyond supervised learning has been a big area of research for us. And it's always been a very interesting, challenging position to work as a researcher in industry, because you have to focus on science, these big breakthroughs, have an impact, but at the same time, it needs to be useful. So we call this, the Pasteur quadrant. It's like you have the curiosity-driven research, you have the problem-solving kind of research, and then you have where we are at TRI, which is really nice, which is we're use-inspired. So we're not necessarily solving the problem that's right now for the next 6 months, but we're listening to all the people that have all these problems and all these products that they contribute to. And then we're trying to extrapolate a little bit beyond in, say, like 3 years or something like that, to say, what is actually the problem that if we hit it at the base, if we work on the foundations, it's going to have a massive impact. Like you're talking about platforms regularly and things like that. It's a bit the same thing, but except with infrastructure, which, was the topic of our podcast. And we talked about the platform of tooling and infrastructure to enable people to do machine learning. Now it's a bit more of the scientific foundations, the scientific platform, the ideas that are, again, going to be largely beneficial for robotics applications. One of the big things we want to do is we want to make useful machines that amplify people. whether they be cars, whether they be robots, or whether they be just programs, and virtualized. Although a lot of the research we do is about physical sensory motor machines, and that's something that is really exciting. I was riding in our car recently, and we have robots in the office that move stuff around, and there's no avoiding gravity and reality and all the kind of problems. Your robot breaks or your car does something bad. It's something real. It's not something
Yeah.
you can avoid. So all these concepts of AI ethics, etc., they're
Grounding.
yeah, exactly. Grounding, embodiment. It's not about a game, Nothing lives in Atari for us. Everything is
Right.
real world.
Right.
Everything is high stakes and safety critical, and we take things very seriously because they obviously matter, because they are made of matter.
Right.
So that's what we do. And so the research wise, scale is kind of important, but we have a kind of a nuanced notion of scale. And maybe you can talk about the data-centric AI there and our positioning there, which is a bit contrarian, I would say. So we could talk about that a bit more if you want.
Yeah, let's just jump right into that. So I think, in talking to folks about data centric AI, my first few conversations, I've been asking folks to kind of define it. And I think everybody has similar definitions, mostly around, to be frank, kind of the way Andrew's framed it, Andrew
Yeah.
Ng.
Yeah, of course.
Um, and when we spoke, as you alluded to, you of course, I think, frame it in a similar way, but you also have some kind of contrarian viewpoints
Right,
around it.
right.
Let's kind of start there. What's a contrarian viewpoint that you have around data centric AI?
Yes. So as a French and a scientist, I love contrarian viewpoints. So let me start with an opening counterintuitive hook, which is I believe that in machine learning we had tremendous progress, and that's why there's so much excitement. And we're really excited about it. And I believe now we know how machines learn, but we don't know how to teach them. And so I think that's what's kind of a bit contrarian and kind of interesting. So let me explain a
I
little
think
bit.
I have a contrarian take that we don't actually know how machines learn, but I will
Ah,
let you continue.
you're even more contrarian than me. You're a honorary French member now. You. um, so okay. What I mean by we know what machines learn is that the genie's out of the bottle. Like deep learning works so well. In 2012, I had done my PhD in video analysis and using very hardcore math, like kernel methods and everything like that. And it had to be convex. It had to have statistical learning guarantees. And then, Krzyzewski arrived, and then the whole world turned upside down. And we entered the age of empiricism, of things that we have good principles or hints, intuitions for why things work. And we manage to make things work even when we don't fully understand or explain. But it does work, and the evidence and empirical evidence is undeniable. And the benefits we received in industry from it, right? Computer vision went from a very interesting problem because it doesn't work to a very interesting problem because it works really well. And how do we go beyond and again beyond and again beyond? We know how machines learn. I agree, it's kind of a fairly bold statement, but there's very few people in machine learning right now that are questioning fundamentally SGD and backpropagation and deep learning. Again, because the evidence is kind of overwhelming. So you want to make something work, you will use a over-parameterized model that you will learn on as much data as you can get with stochastic gradient descent, backpropagation, all the tricks of the trade, and this huge cookbook that we developed through empiricism, right? Through a lot of experimental evidence that we collected over the year that is open because it's open source, that is reproducible. Many different people from many different areas have been building on top of that. So that's what I mean by we know how machines learn. Maybe not the best way they can learn, that for sure, but a way to make them learn, we know. But in the framework of data-centric AI, what I mean by we don't know how to teach them is that building data sets and efficiently building data sets and efficiently teaching machines is not at all what everybody is doing right now. Everybody is just following a simple recipe, which is under the name of the scaling hypothesis, which is bigger is better, right? And we know, I think some people know at least, that bigger is not always better. And there's obviously a trade-off, a fundamental trade-off. I mean, it's a physical fundamental trade-off between scale and efficiency. And so a question is really like, how do we find this trade-off? So there is the scaling laws, which are very interesting, right? It's very hard to estimate. There's some kind of the GPT scaling law versus the chinchilla scaling law. And people tune the hyperparameters in the right way? Stuff we learn in a PhD, which is like make sure your experiments are clean. You study all the hyperparameters, but we have limited computation again. So there's a trade-off between scale and efficiency. So you can't try all the combinatorial explosion of hyperparameters. And then in the end, you make assumptions, and then you have different scaling laws that says, oh, models are much more important. Increase your model size much more for a fixed data set. Versus, you know what, maybe data size and model size is equally important, with all this foundation model research that's going on. But when it takes tens of millions of dollars to do an experiment or train a model, you have to work off of first principles. And I think this is one of the things that characterizes our research is something that I like to call kind of like principle-centric AI, versus it's a bit of a different way than the data-centric AI. Because my definition of data-centric AI is a bit more like focusing on increasing the data, which is, I think what we've seen is not necessarily the best principle.
Yeah, I don't want to spend too much time getting contrarian with your with your
For
viewpoints.
sure.
I don't know that that data centric AI necessarily implies increasing. I think a lot of times the idea is uh, spending more time and investing more effort with your
Right.
data, and often the implication is that you're curating, you're increasing quality, you're reducing the size of the data set as opposed to increasing it. Like fundamentally, I think the contrast is, hey, traditional academic, and Kaggle machine learning is like, hey, we want to solve this problem, get more data,
Yeah.
label it, and throw it at the model, and stochastic gradient descent's going to figure it all out for us.
Yeah. Yeah.
And data centric AI is kind of saying, well, yeah, maybe spend more time on the data.
Right.
And that could involve changing the way you label. It could involve examples that are bad for your model. It could involve using machine learning to, decrease the size of your data set. I think that I think I'm intrigued by principle centric AI. Like I like there's something compelling that the way we approach AI should be based on principles.
Yep.
And one of those principles is actually data centrism. Like we should be thinking about our
Yeah.
data. And so I'd love to hear you elaborate a little bit more about some of
Sure.
the other principles that
Yeah.
drive the way you think about this.
Perfect. Okay. That's great. I mean, you know really what you're talking about because we're getting to the subtle points. I love it. So, okay, let me give you a little bit of no. A good story has some characters. So, let me introduce some characters. So,
Okay.
uh, what is not like I think principles or let's say not the best way. So, there's a couple of different people in the field right now. There's what I call the supervisors. Okay,
Okay.
big tech, people that label a lot, like more data, more labels, and etc. Which honestly is most of the really big successes, right, in deep
Hmm.
learning. So let's call them the supervisors.
Okay.
So they label as much as possible. Again, my idea for that is that I've been labeling things. And in the open world, I think it's an uh, endless pursuit. You're going to label forever. And we want
Hmm.
machines to work for us, not us to work for machines. So I don't think the supervisors are necessarily, it's what got us where we are now, but it's not what's going to get us to the next level.
Hmm.
So I'm not one of the supervisors. Then you have
Okay.
another area, which actually is kind of important for us in driving, which is called another type of characters, which are the geofencers, right? And probably two of them very well known, Waymo, Cruise, and like companies that are doing amazing work in robotaxi, right? So that's what's called like a geofence. I don't know if you've probably heard of this before, but it's basically you're designating an area and some conditions where your machine learning model, in this case a robot, right, is going to design to operate, and how it's going to operate, and you have a safety case around it. And so in safety critical conditions, you build a fence, and you describe inside this fence, inside this playpen, my robot is safe, you know so it's like what I do with my daughter when I put her in a playpen. It's a geofence, it's safe, she can be autonomous there. And so again, I think the geofencers, they're autonomous in the playpen, and it's great, and the whole thing is making the world your playpen. But I think it's also a bit of a challenge because you're trying to turn an open world into a closed world. So has a lot of challenges. So I'm also not a geofencer because I want to work on autonomy. I want something that scales, that learns autonomously, that adapts, and that can be deployed in the world, right? Not just in the playpen. So you have the supervisors, you have the geofencers, and you have the ones that are pretty cool. I call them magicians, but you got to spell the AGI in uppercase in magicians, MAGI-itions, right? And so the magicians are obviously the people that believe in AGI and that believe that all roads lead to AGI. So this is the OpenAIs, the DeepMinds, and a lot of other folks. And especially now with foundation models, people get really excited about that because of the power of language, right? As an API for almost everything. And so the magicians, they believe in the scaling hypothesis. So you're right that the story has multiple different characters that have different interpretations of data-centric AI, etc. The magicians, they really believe that scale is the way to go. And if I train on all of the internet, I'm going to have AGI. And if I train a big enough model on a big enough data set, and I have some safeguards in place, right? So I'm not saying that people just do this recklessly because people now are more wise. Then I'm going to get to AGI. I'm also not an AGI person. I like autonomy more than intelligence because I want robots to be useful. I don't want necessarily robots to be smart. I believe that to be useful, they need to be smart. But I don't want them to be smart for the sake of being smart. I want them to be useful, right? And to be useful, they have to be autonomous. If I have to click on every pixel for every frame of a robot for all my life for it to be able to, help me with, my chores at home, that's not very helpful, So I think that the principle-centric AI that we're thinking about is more inspired by a fourth character, which is my daughter, Cassie. And there was something weird that happened during the pandemic I can talk about, which is I taught my daughter, 7 years old now, how to bike. And I tried for a year before, and I tried it with reinforcement learning, basically, right? Which is basically you put her on the bike, try it, and I catch you. I catch you when you're about to do something, so that way she doesn't pay too bad of a negative reward.
Yeah.
But encourage her when she does well, and all these kind of things. Add some safety guardrails, with the little training wheels, etc. And I tried for 1 year to basically brute force the problem with reinforcement learning. And as we know, reinforcement learning is not really good at sample efficiency, so at learning efficiently. So after 1 year, not so much progress. And then I had a discussion with our CEO, Gil Pratt, a famous roboticist, etc. And he said, oh, check out this method, which is a method called pedal magic. You can find it online. And I'm not going to tell you like details and stuff like this. We could talk about it if you want. But basically, it had some principles about how you learn how to bike, some mechanical principles that actually relate to how cheetahs take turns and use their tails. It's a bit a bit wacky, mechanically speaking, but it has some principles that are physically motivated, physically grounded, and it has an exercise that it derived from these principles, which is basically just a mini environment and a mini training set. And I run my few training samples with my daughter, 5 minutes in this small environment, and then 10 minutes later, she was biking. And I was like, wow, after spending a year trying so much, like giving her so much data, so much guidance, so much supervision. I tried the supervisor's trick, I tried the geofencer's trick, I tried the magician's trick, I tried everything. And then something completely different that was not data-centric AI, because I didn't give her examples that related directly to the task of biking. It was not model-centric AI, because I didn't change the hardware. Like it was same bike, same daughter, same dad. It was everything the same. And so something happened that she learned really, really quickly. And 2 years later, after thinking about it, basically the whole pandemic and like what happened, how do I make machine learning as good as this, as fast at learning and as robust at it? Because she learned on the parking lot, and then we've been biking everywhere. So she's been generalizing out of the domain and all these kind of things that we hope machine learning eventually gets to.
Yeah.
And so this idea of principle-centric learning, principle-centric AI is kind of what emerged from there, and kind of explained also some of the stuff, some of the research we've done has worked spectacularly well, like the sim stuff, the self-supervised stuff, and eventually, we made 60 papers, but half of those papers ended up in production, useful in production. And you're wondering, why aren't the other ones used in production? What happened with these particular papers that actually made a difference in our robust real world? And so you're trying to backward explain. And I found some traces of principles and how we use those principles to either design the data set or design the learning objective. And that enabled like really robust learning, which includes in particular one thing, which is sample efficiency. I think like like, finding the right way to use compute and minimize compute, but at the same time use enough compute to actually learn. So I'm not an AI extremist, neither a maximalist nor a minimalist. It's not about the biggest data set, but it's also not about, short and sweet. There's a good trade-off between scale and efficiency, and was discussed. And I believe that principles is the way to find this trade-off.
Yeah, that's such a great story. Is principle-centric AI the fourth character? Is that
Exactly.
what you call it, or is there another name for that fourth character?
Principle-centric AI is how I think about the research and what we're doing. If you want a name on the characters, I would call us the educators. It's like
Mm.
what we said is that we want to find ways to teach machines, right? We know the mechanism by which we design architectures, we learn with SGD, backprop, etc. But what we don't know is how to make a course.
It's interesting that you say educator and course, because the thing that popped up for me was an element of pre-training
Yeah,
as
yeah.
well as an element of curriculum learning.
Exactly. Yep. Yep. And these words, they're used in teaching in schools. I started to teach at Stanford computer vision, and I hadn't taught a course in a long time. And I co-teach this with Juan Carlos Nibles, who's also a well-known computer vision guy in Fei-Fei's lab. And so we worked a lot on the course. He has a lot of experience, and so I kind of relearned how to teach a course from him. And we taught 100 students, and I taught geometry, computer vision with geometry, which is also a lot of the things we had success in our research for driving and robotics, which is self-supervised learning using geometric principles. And I found that all these parallels between my daughter, between teaching at Stanford, and between our research papers, and as kind of like was really kind of wow. It kind of opened a new world for me of like, oh, can we be the educators that use principle-centric AI to efficiently teach machines?
This is super interesting. So when I think about these different characters, the supervisors think implicitly that the path to AGI, let's say that that's the goal for,
Yeah. Yep.
to
Okay.
generalize. The path to AGI is through human labor.
Yep. Yep.
The geofencers think that the path to AGI, or to whatever the goal is constraints.
Yep.
Maybe Amari can drop it in my doc and I'll remember the name of the episode. But I had a really interesting conversation, or a couple recently, about the role that constraints play in ML. The magicians think that it's, some nebulous notion of scale, which is basically, or another, alternatively or complementarily, self supervision, maybe, is
Yeah,
like
I think
your core
self-supervision is
currency.
one way to unlock scale. It's because you remove the bottleneck to be able to train
Yeah.
at scale, right? So, but it's really scale. It kind of emerges magically from all the data that you're feeding it, right? That's what people get. Like, I'm amazed by DALI, I'm amazed by GPT-3. Who isn't,
Yep.
right? When you see the inferences. But that's the thing, is that what I realize is, why are we amazed? We're amazed because we don't know how it emerged from the data. And if you talk, like, listen to Ilya and all the smart people, right? They're the same. They're like, it's working, because we're feeding it more data, and also because, I mean, there's a lot of secret sauce in feeding the data. So I'm not saying, like magicians, magic doesn't exist. It's like people have these tricks, right? And so there's a lot of tricks to make it work. But so the magicians is really about how to unlock the powers of scale. That's what they're really, really good at, I think. And that's where it's going. But I don't think that's the panacea. That's the end game either.
I get it. I guess the question that I'm trying to get to is like, what is that kind of fundamental one word tool or currency of the educator? Like, what is it that they have, perfected, that is going to be that path?
It's principles. And so basically, okay, there's two types of principles. Let's like answer your question. You said, like, be more precise about the principles. So there's two types of principles. There is the principles you teach, and there's the principles you learn, right? So the principles you teach are things you presuppose, right? So some people call this inductive biases or inductive priors, or you name it, right? But it's basically things you know is true about the world. Newton existed, F equals ma existed. Maybe we don't have to reinvent it. Maybe we can use that prior knowledge, right? I think some of the things that I've listened to Adrien talk about in Datacentric AI is a lot on that, also on like, how do we use expert knowledge, but in a data-driven way, right? So it's not like the going back to expert systems, right? It's about like, how do I, if I know some principles, and it can be ethical principles, it can be legal principles if you have compliance, because there's the AI Act and all these regulations that are coming in AI, and including in robotics space. And so if you have some principles that you want your system to adhere to, right? Be in compliance with, or common sense, like when we talk about embodiment and grounding, that's what we mean. So how do we inject those principles into data-driven learning processes? And then there's the principle we learn from the data. So that's where we train on the data set. And it's not just we're building autonomous prediction machines, right, that are just there to automate the prediction at scale, because that's what machine learning does, right? But maybe what we want to extract is not a bazillion number of predictions, but we want to learn something from what the machine learned itself. And so there's all these cool area of machine learning about machine learning for sciences, etc. Where people are discovering new physical laws, maybe, or finding out, understanding a bit better human behavior. Because if you want to assist and amplify humans, it's not about automation, right? Autonomous prediction machines are there to replace, but if you want to amplify, you got to understand. And so this is the principles that you want to understand from data. So it's a two-way street in a sense. And I can give you some examples of our research where actually this already is happened, right? This is not just principle-centric AI is not just a cool expression, it's actually just a way that I use to kind of define a little bit our successes and what we're actually building at TRI.
Yeah, I do want to transition to that because I think while this philosophical conversation
Yeah,
is
for
really
sure.
interesting, I do want to kind
Right.
of make it a bit more concrete and talk
Yeah, for
about
sure.
some of the things you're doing around self-supervised and
Yep.
synthetic. Before I do that, that episode that I was thinking about was my conversation with David Ha, the benefit of bottlenecks and evolving AI, that was really almost entirely focused on this idea of constraints,
Yep.
not in the geofencing sense, but
Uh-huh.
in more broadly
Yep.
in AI and in other contexts. So your research,
Yep.
where do you want to start there?
Yeah. So
Self-supervised?
self-supervised I think is great. So I think one of the things that we know about the world really well, and that's actually what I'm teaching at Stanford, is geometry, right? When we see the world, when we perceive the world, we have a lot of really good equations. Actually, some of the things dates back like 3,000 years. Back to Chinese philosopher, I think Muzzi, people knowing about the pinhole camera model and all these kind of things. So there's a lot of knowledge we have about how the world works in terms of, let's say, just physics of light, right? And so when you want to do computer vision, how do you leverage that prior knowledge? And historically, it's been in the way of we hand design algorithms, right? We write algorithms that solve the problem based only on our prior knowledge. Now, with machine learning, we want to be data driven. And so we've kind of like thrown the baby with the bathwater and say, well, it's all in the data. And so one of the things, again, as I said, we are always kind of in the moderate route, which is, of course, data is powerful, but of course, prior knowledge is powerful too. So we want to combine both. So self-supervised learning is actually a really good revolution that I'm really excited about, because, and that we've been doing a lot of papers over the year. I think like probably like 15, 20 papers at CPR, etc. I think we're presenting 4 papers at ICRA in a couple of weeks, and 4 papers at CPR, and they're on related topics. And so self-supervised learning is the way where we use these constraints or these knowledge, this prior knowledge about the world, let's say like, the reprojection equations, if you're using the pinhole camera model, and we use that as a learning objective. So in self-supervised learning, you're not solving directly what you want, which is dog versus cat, or detecting a pedestrian or things like that. But what instead you're doing is you're providing a pre-training objective. And so there's 2 big areas. One that I was mentioning now is geometry, where actually it turns out we can solve the task, which for us, it's a lot about predicting depth, how far objects are, because we want to avoid collision with them, or we want to grasp them if it's a robot hand and things like that. So predicting the depth of a scene, turns out you can do that without ever having any supervision. And so this is self-supervised learning for monodef, and something that we have open source code. You can go to GitHub, a TRI page, a repo called PackNet SFM, which has 1,000 GitHub stars. And so it's very popular. People use it for all kinds of crazy things because you can train it only from video. So you can just feed it raw videos, and what it will learn to output point clouds or depth maps from there. And the way it's trained is just by using reconstruction, but not just a black box reconstruction of predict me pixels, and I'll tell you if they look like the pixels you should predict. Instead, it's predict me depth map, and then if you're right, if your network weights are correct, and your depth map will be correct, and then knowing the equations of geometry, we can recreate a past frame from the current frame by warping geometrically using an equation. And then if the warping is correct, the pixels align. And if it's not correct, the pixels don't align. The colors are not the same. And you're wrong, not because geometry is wrong, not because 3,000 years of history, human history in science is wrong, but because your neural net weights are wrong. And then you can do backpropagation SGD. So this is going back to what I said earlier. We know how machines learn. We don't know how to teach them. In this instance, we know how to teach them geometry. We teach them by reconstruction using geometry as an equation in the middle to get the prediction. And then we learn using SGD, backprop, and the way we do it. So we have a bunch of papers. We started from stereo setup with 2 cameras to just a singular camera to now all the crazy sensor suites. And actually we can even, because we've worked on the hardest problem first, which is monocular camera. The reason we've done that is because it's a common denominator behind almost any platform. You have it, I have it in my phone. I actually have more than one camera. Everybody has cameras. Cameras are everywhere. But if you solve the problem well enough for a single camera to predict depth, then you can use it to predict depth for multiple cameras, for cameras that are stereo or not stereo, for LiDAR, for any kind of sensor suite. And that's what we've been doing. It's a very pragmatic approach. It's not to replace everything with a single camera. Some applications might work with a single camera, some definitely won't. But it's to be solving the common denominator. Again, this idea of a platform, the foundations, and building on top of it, right? So self-supervised learning using geometric principles to teach geometry to deep nets is a big thing we've been doing. And I mentioned the second way that you can do self-supervised learning just for pre-training is contrastive learning. You've probably heard about this, had podcasts over this. It's very, very popular. One of the very cool things we've done in collaboration with a really, really good machine learning professor at Stanford is called Teng Ma. We've had a couple of papers at NeurIPS. We had iClear Spotlight and a bunch of papers with them on trying to make sense of self-supervised learning, especially contrastive learning. Why does it work? Because there's all these bells and whistles and these tricks and these cookbooks. And going back to the philosophical discussion about empiricism, we've built a lot of things that work and obviously work. We show that it works, but we don't really understand why. And so understanding why is really important because you have to convince people that are not necessarily ML believers, crazy, woohoo, let's use machine learning just because it's cool, but actually people that need to invest real money and take real risks and putting, say, if you want to save lives, you need to make sure that you have a really good justification that your system will do so. And so understanding things a bit more and the theory and garnering the principles out of the data-driven is really important. And one of the things that I'll highlight there briefly is one of the principles we found from self-supervised learning, which is just contrastive learning. So you do data augmentations because you know that if you change the color of things, it shouldn't change your predictions. So you have all these kind of data augmentations that represent properties like principles of invariance and equivariance that hold true. And you want your system to just adhere to those constraints, again, like in this idea of constraints you were talking about. So you train by just saying when you're out of the constraints, when you're not grounded anymore, when you're making a very weird mistake, right? But you're not telling it what's the solution. You're just telling, stop making weird mistakes. And if you see enough data, it will stop making weird mistakes. And what's going to happen is going to have something that's this pretty good initialization for it may, few shot transfer and like small data kind of cases, maybe some things that in Datacentric AI, you get your experts to label just the right amount. But if you have good pre-training, you don't need more than that. Necessary, but sufficient. So what we found is why does self-supervised learning and particularly contrastive learning work so well? And in particular, a benefit that we found was very surprising is that it's robust. Because you would think if you're in the supervisor's mindset, that's, okay, Adrien is saying supervisors is bad, but it's just a matter of cost. If you can pay the cost, if your return on investment justifies labeling forever, just label forever and it's the best thing to do, right? Wrong. Because actually we know that if you just collect, data has bias, natural data has biases, right? And if you just label more and label more and label more, you're going to create distortions, you're going to have human biases injected in the labels, mistakes, or, you're going to label more the mode and all these kind of things
Right.
that yields issues.
Yeah,
So,
particularly in your case in AV, where you're collecting a lot of data of the usual thing happening, but the
yeah.
problem is all about the corner cases that don't happen very frequently.
Ding, ding. Exactly right. Yep, absolutely. And so self-supervised learning, what we found surprisingly, is more robust to the imbalance. So if you collect data at scale, it's very imbalanced. You have this long tail of edge cases and rare conditions, rare events, as you mentioned, and some of them are noise, but some of them are really bad. Like, you really want to make sure they're very important for you to know and learn. And so, but you can't tell from just the data itself. It's just rare events, right? And so what we found is that self-supervised pre-training is actually better than training with labels, because it's more robust to the long tail, to the imbalance. And we were like, okay, cool, another empirical fact that self-supervised learning is a good idea, but why? And in this paper that we actually just presented at iClear as a spotlight, we found the explanation and the principle for why. And it's a bit counterintuitive. So what we thought was that when you do self-supervised learning, you learn more from the tail. You learn richer features, better features from the tail, because the label is not leading you astray. Take an example of driving. You drive mostly straight, and then you have all these kind of weird maneuvers, evasions, etc. And so when you drive straight, and you say drive straight, that's your label, basically. The model might just collapse on the mode, right? It might just say, oh, just drive straight all the time. That's enough to minimize my loss. The rest is just weird. There's no pattern, right? And so if you just do supervised learning, this is what would happen. But if you do self-supervised learning, our assumption was it generalizes better, it's more robust, because it's going to learn more. It's going to have to try to explain or reduce the loss on the rare things too. And so it's going to learn better features from the tail. But what we found out is that it's not true. It actually learns better, more diverse and more generalizable features from the mode. And let me give you an example and so we have like very cool semi-synthetic experiments in the paper, a bit hard to explain, but you can look at it. So where we basically just probe this and verify this, both with theoretical explanation and with like controlled experiments to show that our principle, that our explanation is correct, not just that the performance is good, but that's also, we know why. But let me give you an example. If you want
Before
to,
you do that,
yeah,
is the specific case you're referring to the uh, self-supervised by you've got some geometric relationship and you're projecting through that, or is it the data augmentation contrastive
yeah,
learning
it's the
case?
contrastive case. So for this
Okay.
particular paper, we found that it's the contrastive case, because for the other case, we know the principle because we teach by principle, right?
Mm-hmm.
The contrastive one is more the other way around. I mean, there's this principle of invariance, but we wanted to know why does it work, and get the principle out from the model after training and why it works, right? And so this principle is it learns better features from the mode, because, like, the example is, if you learn to drive straight, right, all the time, and you say drive straight, you're basically ignoring things that happen behind you. So I don't know if you've when I came here, in Europe, we jaywalk. It's like we cross the street whenever, again, maybe the French, maybe that's just me. We cross the
I'm
street when
from
we
New
want to.
York. We also jaywalk.
There you go. But you typically don't jaywalk right in front of a car, right? You typically wait for the car to go and then you just cross, right? So the
Yeah.
jaywalkers are always behind the driver. So when you're learning to drive, you basically can safely ignore the pedestrian in the back. It's not going to affect your policy. So if you're very focused in the supervisor's way or the geofencer's way, you're just saying, all right, just focus in front of you, and just what matters is avoid collision in front of you. But in a self-supervised way, you will say, oh, something weird happened behind you. And I don't care about you learning the policy. I care about you satisfying the contrastive learning objective. So you have to understand the world. You have to explain what happened behind you. You have to verify your invariance and equivariance properties also on what happened behind you, if it's part of your input signal, right? And so then you will see basically jaywalkers, and you will have to learn features about these jaywalkers, even though they don't relate to directly optimizing your end goal, which is, in this case, would be drive straight. And so now, linking back to my daughter Cassie, I try to teach her biking by teaching her to bike. But when I taught her the principles about biking, right, about how not to fall, basically, then she learned how to bike because she had internalized the principles. And it's basically the same thing here, is that it internalized the principle of you have to explain what's happening around you, because you never know. Someday, that jaywalkers that you've seen behind you, they might actually cross in front of you, and you need to be able to represent them. Because if you don't represent them, if they're not there in your feature representation, you're not gonna be able to react to them. And so that's what we found, this counterintuitive principle, which is it generalized better, self-supervised contrastive learning generalized better not because it captured better features from the tail, from the rare events, but because it captured more diverse features from the mode. Because all kinds of things happen around you all the time. And in the mode, you have equal diversity because you're still experiencing the same crazy world. It's just that the long tail of actions, right, does not correspond to the long tail of events, of things that happen in the world.
Did you find a way to control for this idea that the reason why you had increased robustness isn't necessarily that the model was, learning about the things in the rearview mirror, but rather just that you gave it multiple things to do. And so in this, based on kind of what we've learned about multitask, like just having the model doing multiple things independent of what those things are, it creates some robustness.
Yeah, I think I encourage people to have a look at the paper because there's a very cool visual experiment that validates. So there's some theory, right? And I mean, of course, with assumptions that not necessarily reflect all the practical applications and successes as usual, but under some considerations, some constraints in my hypothesis, we know why and we can prove it. And then we have some visual experiments where we showed that basically what you do is you have an image where you have the left side that has the category that corresponds to the label, and then the right side that has a confounder or even just a black, like a black image. And so then what you do is you train on that. So you basically introduce a confounder, and then at test time you remove that confounder or you swap it. And then what you want to see is well, at training time, the supervised way, it will have just focused on the half part of the image that corresponds to the labels because the rest is noise. But the self-supervised part, it trained on both sides and it learned features from both sides. And then when you apply it on the test time where you said, oh, now I changed the environment and the relevant part is not on the left, it's on the right now, then the self-supervised feature says, no problem. It's still things I know how to represent. Whereas the supervised part is now very causally confused, right? And causal confusion is just one example of like how spurious correlations affect very negatively supervised learning and the supervisor's way. And that's why it's the same thing as the supervisors and the geofencers. You're just running after a fact that the world, there's only one thing that's constant in the world is change. Which is why you just label forever, and then you're growing your operational domain, and the world changes, and most likely your system has to change also. So this is why the self-supervised learning is all about learning from diverse data in a diverse way. This is the quality and diversity of data in the data-centric realm, which is still a bit more art than science, and that's where our research is like you said, data centric is not necessarily just about scale. It's about focusing on the data and being better about using the data, designing data sets, and etc. But as you know, it's still very much more an art than a science, and we're trying to make it more into a science by using principles.
In the paper that you were describing, was there a synthetic data component to that, or is that separate research?
The synthetic data, it's a different set of research where the idea is there are certain sets of principles. We don't exactly know how to include them in the machine learning pipeline, right? Whether via the data augmentation that I mentioned, like contrastive learning, or whether via the self-supervised objectives that I was mentioning. And the big one is that relates to grounding and embodiment is physics, right? So we don't know how to have F equals ma into a deep net, right? We don't know how do you make the connections? Which way do you we don't know how to do that, but we know it's true. We know gravity, and we want grounding into these systems, and that's the whole embodied AI area. And so, but what we know how to do is we know how to program it into simulators, and simulators are basically a huge opportunity for dataset generators. Something what we call programmable data. You write a program, and this program generates you data sets, and these data sets are actually generated according to principles because they're actually generated according to a program that is written by humans that represents our prior knowledge. Again, F equals ma and all these kind of things. So a lot of the things we've been doing, which originally came out of necessity because sometimes you don't have the data, like for accidents or for things that are, like things you want to react to and you want to anticipate, but collecting that data would be unethical, or it's too rare, or it's impossible. But yet you want your system to be able to handle those cases. So synthetic data is a great way to do that because you can program those principles into the dataset generator, and then you have basically built problem sets, you've built a curriculum, you've built a set of exercises, right, for your machine learning model to digest and internalize the principles in its own way, in its weights. So you program in human language or human code F equals MA, generate a lot of images and videos that then you feed through the usual machinery. Again, we know how machines learn, SGD, backprop, etc. But this time we know how to teach. We teach through a simulator that is a data set generator, essentially.
Yeah, yeah. In a lot of ways, there's kind of a unifying idea between that and the use of geometry
Yep.
that we were referencing before. It's we've got some set of knowledge or heuristics about the way the real world works, and we use that to generate data, and then use SGD and the techniques that we've proven out. It's kind of interesting, kind of reflecting on the evolution of the industry. And I've talked about this ad nauseum. Folks who've listened to the show for a while probably know what I'm going to say, but like, we started out, you referenced your early work in computer vision. We had all of these, ground up rules and, equations that, we built everything around, and it wasn't statistical at all. We kind of swung the other end of the pendulum, and everything we wanted to be statistical, and throw out the rules. We get enough data and the system will learn the rules on its own. And in practice, it doesn't really make sense to throw out all the rules. And so you've had, I think, some attempts at like, how do we fuse a real world based model with a statistical model. But I think what in this conversation, both in terms of the use of geometry as well as the use of synthetic data, it's another approach, which is, well, let's just use the rules to create data or labels, and then use the statistical approaches.
Exactly. Yeah, I couldn't have put it better. I mean, it's basically we're in the age of reason now. It's like there's always the pendulum swings one way or the other. We know everything, we can program everything, logic, etc. Which, by the way, was doomed to fail. We knew it from theory, from Kurt Gödel, right? But then there is the other swing of the pendulum, like you said. It's like throw it all away. It's all in the data, and honestly, the reason is also because it's easy. I mean, it's hard to make large scale systems work, but conceptually, it's just scale things up, right? And now we're in this realm where how do we get the best of both worlds? Because nothing is all good or all bad, right? There's always this gray areas, and so finding the best of both worlds, as you said, which is how do we use our knowledge, how do we use a data-driven approach, and how do we combine them together? And what I was trying to explain is that there is the using the rules to generate the data, as you said, using the rules to generate the supervision, and of course, there's all this prior knowledge that goes into the model architecture. Although now we're kind of realizing that the model architecture, we have powerful generic model architectures. So I believe that the data-centric and the self-supervision side, I think those are really where I'm excited the most about, and most of our research is.
Awesome. Awesome. Well, we've been digging deeper and deeper, and I feel like we're still at a fairly high level, and there's so much more. I'd love to, talk through exactly how you're doing synthetic data and just go into a lot more detail. We don't have time for that this time, but maybe we'll be able to get you to TWiMLCon, which will be in the fall, to, share a lot more detail. But until then, or, we need to speak more frequently than every
Yeah.
3 years. Uh, but all
Yeah.
that notwithstanding, it's been a pleasure having you on the show, Adrien, and great chatting and learning about what you've been up to.
Likewise, and yeah, it was very high level, but we have like I think like 20 papers this year, and they're all on my website and etc. So people dig in. Feel free to ping us. Come to ICRA, come CPR. Conferences are a thing again. Looking forward to TWiMLCon and chatting with people live. And yeah, looking forward to talking again. Hopefully not in 3 years.
Yeah. Awesome. Thanks, Adrien.
Thank you, Sam.